So in this section, we're going to take a look at chord of contact. And before we get started, right, let's actually check out what a chord of contact actually is. So here we have a standard parabola given by x squared equals to 4ay. And let's say that we've got an external point, say t, okay, and its coordinates are going to be given by x0, y0. And what I can do with this external point is I can draw two tangents from this external point to my parabola, okay? And the points of contact, right, these 2 points over here where the tangents intersect with the parabola, that are called the points of contact. If I label this as A and I label this as B, and if I join them together, this resulting chord, okay, I know that's just a chord because it's just a line joining 2 points, but because of this specific geometric setup, AB is known as the chord of contact, okay, because it's the chord that joins the 2 points of contact together. Now, let's just say that A is given by x1, y1, okay, and let's say that B is given by x2, y2. The chord AB, okay, so the chord of contact AB in this case is going to have equation x0 is equals to 2a times y plus y0. Okay, that's going to be the standard equation. And the weird thing about the chord of contact is that the proof is actually not necessary. So whenever we actually need to use the chord of contact formula for extension 1 math in parametrics, we can go ahead and just quote it. So out of all the formulas that we've looked at, so the equation of the tangent, equation of the normal, right, equation of the chord, they all have to be proven whenever we need to use it. The only exception is the chord of contact. You guys want to use the chord of contact equation, then you guys can go ahead and quote it straight away, right? Of course, A is still the focal length. x0, y0 are the coordinates of your external point, t. Now, the proof is not necessary, but if you guys want a brief rundown of what the proof actually looks like, okay, because for students who are actually doing extension 2, and when you guys get to conics, okay, like conic sections such as parabola is essentially a conic section, okay, but we don't really look at it too much in extension 2. But other conic sections, for example, the ellipse, the hyperbola, and stuff like that, extension 2 students are required to know how to prove the chord of contact, okay, but for extension 1, it's not necessary. But if I just give you guys a brief rundown, the idea looks something like this, right? We start off at A. So we're going to start off by looking at the tangent at A. And what you guys will realize is that the tangent of A is given by x1 is equals to 2a times y plus y1. Of course, if you guys haven't realized yet, while dealing with the Cartesian equation, okay, there's no parametric form for the chord of contact, right, for extension 1 math or extension 2 math. So the tangent at A is going to be x1 equals to 2ay plus y1. And then what we're going to say is that the tangent at A is going to pass through t. Okay, so in other words, if I take x0, y0 and I substitute it into this equation, left-hand side and right-hand side needs to balance. Okay, so since tangent at A passes through t, given by, of course, x0, y0, then we can say that x0 times x1 must be equals to 2a times y0 plus y1, and this is an identity, right? And similarly, if I look at the tangent at B, which is given by x2, is equals to 2a times y plus y2, we can say exactly the same thing, okay? So since tangent at B, right, also passes through t, right, given by x0, y0, then we can say that x0 times x2 is equals to 2a times y0 plus y2. And what happens is that when we look at these identities, we realize that they look pretty much the same, right? Where they change, okay, or where the two identities differ is that the x1, okay, becomes the x2 in the second case, and the y1 becomes a y2 in the second case. And the idea behind the proof requires you to know that when we're looking for the equation of a line, okay, 2 points define a unique line. So when I look at the equation xx0 equals to 2a times y plus y0, this must be the equation of the chord of contact, right? Or in other words, the line that passes through A and B. Because if I take a look at this equation, if I substitute the coordinates of A, x1, y1 into this formula, I get x1 times x0 equals to 2a times y1 plus y0, which I know is a true statement because that's just identity 1, which we know is a true statement. Similarly, we know that this line over here also passes through B, given by x2, y2, because if I sub x2 into x and y2 into y, I get x2 times x0 is equals to 2a times y2 plus y0, which I know is also a true statement because that's just identity number 2. So therefore, if I've got a line that passes through A and B, that line must be given by xx0 equals to 2a times y plus y0, because this equation satisfies, or rather the coordinates of A and B satisfy this equation. Okay, and if I know that I've got a line and both points satisfy the equation of a line, then the equation of AB must be given by xx0 equals to 2a times y plus y0. Okay, and that's all we have for the proof of AB, right? Except there are a lot more words over here which I'm not writing out because I essentially said them while I was reasoning it out. So if you wrote all those words out, okay, I guess a slightly more simplified fashion will do, okay, and that will serve as the proof for the equation of the chord of contact AB. Okay, but do take note that this proof is not necessary. Okay, whenever we want to use this equation, we can just quote it straight away. Okay, so let's check out some examples to see what we can actually do with chords of contact.